So, hello students, very good to see all of you. In the previous class, we had looked at some applications of the GEOFEM program for the analysis of bar element structures with bar elements, and let us continue on the same thing and see some more examples to illustrate how we can use this program. And the first example is the same plane frame or plane structure that we had seen earlier, that has 3 nodes and 3 bar elements, and the way we saw it, the left hand side support is on a hinge where you do not permit both x and y direction displacements, whereas the node 3 is supported on a roller. It can translate horizontally or in the x direction, but cannot move in the y direction. And let us see what happens in some other boundary conditions. Let us say that you have this structure built in a highly mountainous terrain, and the right hand side support is on a slope. So, you want to provide the roller parallel to the slope on the other side, and so we will have a problem because we did not discuss that, because all the cases that we considered, the boundary conditions were applied in along the Cartesian coordinates along the x and y axis, but now we want to apply a boundary condition here saying that you have a roller that is at an angle to the horizontal, at an angle to the x axis. This type of boundary conditions we call them as skew supports or the skew boundary conditions, and in this case this roller is at an angle of 45 degrees to x axis. So, how do we do it? And I will illustrate that using our bar elements, and then we have spring elements that are connected between 2 nodes, and we can exploit their features. So, what we can do is we create an additional node 4 at the same location of node 3, that is at x is equal to 5 and y is equal to 0, so that we can introduce a nodal link element here, and then we create another node, an extra node 5 at x is equal to 10 and y is equal to 5 at 45 degrees from the node 3 along this line, so that we can define the tangential direction for the spring element, because the spring is connected between 2 points that have the same coordinates. So, we cannot really define any direction for that, and just to be able to define the directions, we give 2 additional nodes that are placed apart from each other, and then now we make this node 3 as a free node. So, previously we had the node 3 with the free x direction degree of freedom, but along the y it is fixed. But now this node 3 is completely free, and then we connect the node 3 and node 4 with some shear and normal springs, and the shear spring has a stiffness of 0, so that the system is free to slide along this surface, this inclined surface, and the normal stiffness is given very high value, so that there is no deformation in the normal direction to this inclined surface. And we can run the program, and these are the results that we get. See, the ux and uy at node 1 are 0 because this is on a hinge, and the displacements at node 2, now they are slightly different, and at node 3 is actually this entire structure has rotated around, because this is free to move along the downward direction here, and because our surface is at 45 degrees angle, both x and y direction displacements are the same at node 3, 3.66, 3.66 in the negative direction. And when we calculate the element forces, we see that both element 1 and 2 they have the same forces. Element 1 has a tensile force of 100 and element 2 has a compression force of 100, and then element 3, previously it had a tensile force of 50. See, that is element 3 has a tensile force of 50, but now it has a force of 36.6 and that too in compression. See, actually the nature of force in element 3 has changed from being tensile to compression because of the change in the boundary conditions. So, here our boundary condition is different. So, the entire structure has rotated and it has induced some compressive type deformation in element 3. So, we have this negative force. Okay. So, it's actually it is the spring elements can be used for even applying skew boundary conditions, and later we will see that these spring elements can be used for modeling the interfaces between two surfaces and so on. Okay. And now let us look at the data file corresponding to this analysis. So, this is the data file for this analysis. Okay. So, previously we had only 3 nodes in this problem. Now we have 5 nodes, because we need some extra nodes to introduce the spring elements and then to define the direction of this the tangential direction. So, I have defined node 4 with the same coordinates of x is equal to 5 and y of 0, and then I have eliminated all the degrees of freedom in that particular node, and then there is one more node defined at 10 and 5, node 5, okay. And these are our bar elements 1, 2 and 3, and then this is the spring element. This node the type 5 in the GEOFEM program refers to the nodal link elements, and there is only one nodal link element, and it is connected between nodes 4 and 3, that is at the right hand side support, and then the two external nodes are 4 and 5. See, the 4 is at x is equal to 5, y of 0, and node 5 is at an inclination of 45 degrees. The x is 10 and y is 5, okay. And then we applied the 100 kilonewton force, okay. And now let us see what happens. So, these are this is the result file. Okay. So, here this is the definition for spring elements. The tangential stiffness is 0 and the normal stiffness is 10 to the power of 10, so that there is no deformation normal to the surface, and then these are the deformations, and then the forces and the bar elements, and the element 3 has a compression of 36.6, and then when we look at the force in the spring, it is coming as compression 122.47. See, previously when our roller support was on horizontal flat ground, it was 86.6, and now we are getting 122.47. But then if you multiply with sin 45 to resolve it in the vertical direction, we will get back our 86.6. And let us see one more thing for a flat surface. Let us see, let us define the node 5 along the horizontal direction, along y of 0 corresponding to the 4th node, and see what happens. So, here I am defining both node 4 and 5 along the x axis, x of 5, y of 0, x of 10 and y of 0. Okay. And then you see here we get back our previous result of the 50 kilonewton tension in the element 3, and node 3 has extended by 5 millimeters. Okay. And then the normal force at node 3 is 86.6, because that is the reaction force that we should expect because of the applied force. Okay. So, this example actually explains how we can use the nodal spring elements for simulating skew boundary conditions. So, otherwise we have to go through some transformation at the stiffness matrix level, but that is not implemented in this GEOFEM program, but an option is given to implement the skew boundary conditions through the boundary spring method. So, let us continue. So, now let us look at one more problem, and this problem is the case of one dimensional bar element. It's a column with a load, and the solution for this is delta of PL by AE. But only thing is our cross section is not uniform. It is a tapered bar having an area of 0.5 at the top and an area of 10 at the bottom, and you please mind that this is not a scaled diagram, just it's shown with some taper, but then it's actually the taper is much larger, because the area at the top is only 0.5, whereas the area at the bottom is 10. So, you can imagine how much should be the diameter at the top and bottom, and just for simplicity I have given straight lines, but it is not really a straight line. Okay. And then it's a simple one dimensional problem with loading at the top. And how do we do it? Because in our stiffness formulations, we did not consider the varying cross sectional area of the bar elements. We assume that the bar elements have the constant cross sectional area, and then the constant properties E, so that the stiffness of the bar elements can be written as AE by L. And what we can do is we can split this entire length into some convenient intervals, like some number of elements, and calculate the average area from the areas at the two ends, and then use that as the area for that particular element. So, here element 1 is at the top, area is 0.975, 2 is 1.925, and so on. And so, on the left hand side you see another mesh, but with smaller number of elements. So, this mesh has 10 elements and then 11 nodes, whereas this mesh has 5 elements and 6 nodes. So, here you see this the jump between the two elements is larger compared to here, and the tapered cross section we can simulate by having a series of elements each having a different area, and as we are approximating this tapered section with the uniform cross sections within elements, the more number of elements that we consider, the more accurate is going to be the result. Okay? And finally, we can compare our finite element results against the exact theoretical result just for comparison purpose. And here on the left hand side, see this total length of 10 is divided into 5 elements with a delta L of 2, and E is 10,000. On the right hand side, we have a mesh with 10 elements and delta L of 1. Okay? And so let us look at what happens. And the theoretical solution is given like this: PL by A2 minus A1 E ln of A2 by A1, and for particular properties of A1 of 0.5, A2 of 10, and L of 10, E of 10,000, the applied load of 25. And the exact solution is this 7.8835 times 10 to the power of minus 3. And you might wonder what happens if we flip the areas, like let us say we put A2 there and A1 here, but we get the same solution. Like you can try it out, you can change A2 and A1, but you will get the same result. And the corresponding solutions with finite element analysis with 5 elements, it is 7.145 times 10 to the power of minus 3, and with the 10 elements it is getting closer to the theoretical solution, 7.60 times 10 to the power of minus 3, and then with the 20 elements 7.79 times 10 to the power of minus 3, whereas the exact solution is 7.88 times 10 to the power of minus 3. Okay? And actually, as you see here, as we increase the number of elements in the mesh, we are moving closer to the exact result, and with the smaller number of elements we get a lesser displacement. So we can, in other words, we can say that our response is stiffer. See, with lower number of elements we are predicting lesser displacements. So that means that our response is stiffer. Okay? And as we are increasing the number of nodes and number of elements, we are approaching towards the exact solution. And just for comparison purpose, I have given you the solution with Rayleigh-Ridge method by considering only one admissible term. U of x is A1x, and the solution is like this. The average area A1 plus A2 by 2 is considered for in your delta of PL by AE equation, and that is that's way different from the exact solution. Let us look at the data files for this. Tapered bar. Okay. So actually this is our data file for this problem. So actually when I give you these data files for your running, I will put in some comments so that it is more easy for you to understand, and then you also please refer to the GEOFEM manual. It is a very short manual, it is only some 20 pages. And so here we have 11 nodes, 1 to 11, and then have deleted. It is a one dimensional problem with the displacements only along the y direction. So in the boundary conditions itself I have eliminated all the other degrees of freedom. At node 1 we are allowing the vertical displacement. At node 11 it is a fixed node, and then node 1 is at height of 10, y of 10, and node 11 is 0. Then automatically in between the nodes 1 and 11, the intermediate nodes are generated, because we have put a 1 here, that is the that's the increment for generating the missing nodes, and we have 10 elements and E is 10,000, and the element 1 is connected between nodes 1 and 2 and the area is 0.975, and the element 10 is connected between nodes 10 and 11 and the area is 9.525, and then once again the elements between 1 and 10 are automatically generated. So, if we give 1, then the next element it generates is 2, 3, 4, 5 and so on, but if you give let us say 2, then it will generate the 3, 5, 7, 9 and so on. Okay. And then at node 1 we have applied a load of 25. Okay. So, it is just to compare this with so this is the mesh that we are considering. There are 11 nodes. Node 1 is at a height of 10 and node 11 is at a height of 0, and then node 1, 2, 3, 4 and so on, and element 1 has an area of 0.975, whereas element 10 has an area of 9.525, right. Okay, so that is 0.975 and 9.525, and now let us look at the result. Okay, right. So, here we gave the data only for nodes 1 and 11, and all the intermediate points are generated automatically, and you see that no degree of no equation number is assigned for displacements in x direction or the rotation, because this is a bar element and only y direction displacements are defined, and the element modulus is 10,000, and then element 1 is connected between nodes 1 and 2, 2 is between 2 and 3 and so on, and you see here our area is also proportionally increased 0.975, 1.925 and so on, and element 10 has an area of 9.525, right, and then these are the displacements at different nodes. At the top is 0.0076, 7.6, that is what we saw, times 10 to the power minus 3, and these are the axial stresses. Okay. So, it is actually these one dimensional elements, they do not have the preprocessor, but then it gives an option for generating the missing elements and nodes. If you just give for node 1 and node the last node, and in between we can generate, and the same for elements. Okay. So, now let us continue. So, we see that this approximation with finite element analysis tends towards the exact solution as you increase the number of nodes and number of elements in the mesh, right. So, now let us move on to beam elements, the use of beam elements, and let us consider a very simple single story frame like this, and it has 4 nodes, node 1, 2, 3 and 4, and we have 2 columns and then 1 beam. Let us say that the columns are of dimensions 400 by 400 millimeters, and these columns are made of M40 grade concrete, and the beam has a width of 400 mm and a depth of 800 mm, and it is also made of M40 grade concrete, and the height of the building is 4 and the width is 3.5, and then there is a lateral load of 25 applied at this point, and these are the displacements and rotations, and then the forces in the beam shear force and bending moment, and then forces in the columns. The column will have predominantly axial, and of course there will be some shear and bending moment, but I have not shown here. And what happens, so when one of your supports undergoes some relative settlement? Because previously when we applied some settlements for our truss structure, the settlements had no effect on the element forces, because all the joints are hinged connections, so we can the structure can freely rotate and then accommodate the deformations without increasing the forces. But then here we have it's a statically indeterminate structure, and then all the node points, they are rigidly connected. So if you subject a support to some deformations, then it will lead to some additional shear force and bending moment in the elements, and that is what we have seen. See here, the right hand side support is assumed to undergo a settlement of 25 millimeters, and then when you calculate the shear force in the beam, is 53.3. The blue one is without the settlements, it was only 13.97, and bending moment now is 93.4, and without settlements it was only 24, and the axial force in the columns is also very high, 53.3 versus 13.97 without the settlements. So that shows the effect of settlements on any indeterminate structure like our building frames. And also one important point or one important lesson that we learn is, if your structure is going to undergo any relative deformations, we have to take care of the additional forces that are generated, additional shear force and then additional bending moment. So that we can provide sufficient steel reinforcement to prevent the cracking. I think that may be the last one, and let me show you these data files. So this is our data file. See, there are 4 nodes, and I purposely did not constrain any of these nodes at the element level or at the assembly level. So all the degrees of freedom are given as 0, so that it will number them. Node 1 at x of 0 and y of 0. Node 2 is at x is 0, y of 4. Node 3 is at 3.5 and 4, and node 4 is at x of 3.5 and y of 0. Then we have 3 elements. Then Young's modulus is calculated as 5000 times square root of FCK, and this is our modulus, and the cross sectional area for the columns is 0.16, 0.4 times 0.4, and then the moment of inertia 1/12 BD cube, that comes to this much. Then for the beam, the cross sectional area is 0.4 times 0.8, that is 0.32, and then this is our moment of inertia 1/12 BD cube. Then a load of 25 is applied at node 3 along x direction. So this 1 corresponds to x direction, node 3 is this, okay. And then all the degrees of freedom at the 2 supports, node 1 and node 4, they are constrained, okay. And let us look at the results. So this is the result file. These are all this is the nodal coordinate data. There are totally 12 degrees of freedom, and then the beam element data, cross sectional area, moment of inertia, shear area. Actually, as I mentioned, the shear area is taken as very large value, so that these elements become pure flexural members. And these are the results, the displacements, and then the beam element forces, axial force, shear force and moment at the two nodes, because each element has node 1 and node 2, and these are the axial and shear and moment. Then these are the reaction forces, and since we applied a force of 25 in the positive x direction, the reaction force in the x direction is also coming out as minus 25 for equilibrium. Then in the vertical direction there is no force applied, so the sum total of the reaction force is 0. But then if you see, the node 1 has minus 13.97, whereas node 4, that is at the right hand side, it has an equal and opposite force plus 13.97, so that our net y direction reaction force is 0. Okay, and I think the same thing with settlements. So this problem is the same as the earlier one, except that we specified a settlement of 25 millimeters at node 4 at the right hand side support, and these are the settlements, like at node 4 y direction displacement is minus 0.0025, and then these are the shear forces and bending moments and so on. These are much higher than what we had when we did not have any settlements. So this example, it shows you the use of beam elements, and when we see these files, I am going to put some comments so that you understand what each line of the data means. Okay. So this is how we can utilize the spring elements, bar elements, and then the beam elements for some practical analysis. And in your tutorials, you will have some problems that you need to solve by hand, and then you can compare your hand calculations with these analysis through the finite element program, so that you can check whether your answer is right or wrong. Okay, so thank you very much. I think this may be the last slide, and if you have any questions, please contact me at this email address, and I will respond back to you at the earliest. Okay, so thank you very much.